And now in this lecture we'll answer on two questions. In the first question, we'll find out the area of rectangle ABCD that blocks this circle, and in the second question, we find out the area of this trapezoid ABCD. So we start with the first question. In the drawing, we have rectangle ABCD. This rectangle ABCD blocks this circle, or the circle is inscribed by rectangle ABCD. In addition, you know that this is called EF, that is equals to 12 units in its length. This is line segment FG, that is equals to 10 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, we will define the radius of this circle as R, and here we have those 2 points, the point of tendency of tangent DC with this circle. This point is point N, point M, and the point of tendency of tangent AB with this circle, this point is point N. We will join points O and M together by a straight line. Point O is the center of the circle, point M is a point on the circle itself, therefore OM is the radius of the circle. This is equals to R according to our definition. The radius OM is drawn to point M, that is the point of tendency of tangent DC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we'll join points O and N together by a straight line. ON is of course the radius of this circle that is equals to R. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. We will define the length of tangent A. We will define the length of rectangle ABCD as AB. AB is the length. And we define the width of rectangle ABCD as AD. AD is the width. We join points O and E together by a straight line. OE is of course the radius of this circle that is equals to R. Again, because of the fact that the radius OE is drawn to point E, that is the point of tendency of tangent AD with this circle, and whenever your radius is drawn to the point of tendency, then tangent AD will be perpendicular to the radius EO. If AD is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. By doing this construction, we get a deal quadrilateral DMOE. Inside quadrilateral DMOE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces angle must be equal to 90 degrees in its size. Likewise, we'll focus on the lower quadrilateral EONA. Inside the lower quadrilateral EONA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees, according to the same rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces angle must be equal to 90 degrees in its size. So the size of the big angle MON is equal to 90 degrees plus 90 degrees, that is 180 degrees. So write it down. The big angle MON is equal to 180 degrees in its size. And you know that any angle that is equal to 180 degrees in its size must be a straight line. Therefore, MON is a straight line, or line segment MON is a straight line. But if MON is a straight line, then MN is of course also a straight line. So write it down. MN is also a straight line. But MN is a straight line that touches the circle at 2 points, point M and point N, and therefore MN is a chord that passes from point O, that is the center of this circle, and know that any chord that passes from the center of the circle must be the diameter of the circle. Okay, so MN is a chord that passes from the center of the circle Therefore, MN is the diameter of the circle. MN is the diameter of the circle. In the next step, So I wrote here that Mn is the diameter of the circle. Mn is the diameter. Anyway, Mn is of course a straight line, and therefore this shape DMNA consists of 4 sides, and therefore shape DMNA is a quadrilateral. So write it down. Shape DMNA is a quadrilateral because it consists of 4 sides. It's a quadrilateral that has 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we relate to the big quadrilateral DMNA as a rectangle because it has 4 right angles. Therefore it is a rectangle according to rule 5. So this big quadrilateral DMNA is a rectangle because it consists of 4 right angles. It is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side DA. Okay, M in rectangle DMNA side MN must be equal to the opposite side DA. MN equals to the opposite side DA. But DA itself is the width of rectangle ABCD. So can I tell that DA is the width of rectangle ABCD? And we also find out that MN is the diameter of the circle. So you can write here that MN is the diameter of the circle. So in total we should find out that the diameter equals to MN, the diameter of the circle equals to MN, and MN equals to DA, and DA is the width. Okay. In the next step, we will extend the radius EO by a straight line until it touches the circle. And we will define the touching point of the extended radius EO with this circle. This point is point L. When you extend a straight line by straight line, the result is a straight line. So EL is a straight line that touches the circle at 2 points, E and L. Therefore, EL is a chord. EL is a chord that passes from point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. So in conclusion, we found out that EL is the diameter of the circle. So we're going to write here that EL is also the diameter of the circle. We can add here that EL is also the diameter of the circle. EL is the diameter of the circle, and from this long equation, EL equals to the diameter equals to MN equals to DA equals to the width. We will derive that EL is the width of rectangle ABCD. And again, we found out that from this long equation, that EL is the width of rectangle ABCD. EL is the width of rectangle ABCD. So write it down here. EL is the width of rectangle ABCD. In the next step, we'll join points L and F together by a straight line. By joining points F and L, we create peripheral angle EFL. So write it down that EL is the diameter of this circle. Repeat again, by doing this construction, we created here peripheral angle EFL that subtends on EL, that is the diameter of the circle, and we know that according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. So repeat again on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees. So in the drawing we have a circle. AB is the diameter of the circle. This is peripheral angle ACB that subtends on AB, that is the diameter of the circle. And according to this rule 7, peripheral angle ACB must be equal to 90 degrees in size because it subtends on AB, that is the diameter of the circle. So we can implement rule 7 in our drawing. Or because in our drawing, we have peripheral angle EFL that subtends on EL, that is the diameter of the circle, and therefore peripheral angle EFL must be equal to 90 degrees in its side according to rule 7. In the right triangle EFL, we will define this angle E as alpha. So in the right triangle EFL, this angle equals to 90 degrees, this angle equals to alpha, therefore this previous angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we will do another construction. That is to say, we will extend the diameter EL by straight line until it touches side CD of rectangle, until it touches side CB of rectangle ABCD. Repeat again. We will extend the diameter EL by straight line until it touches side CB of rectangle ABCD. And we define the touching point of the extended diameter EL with this side CB of rectangle ABCD. This point is point C. EL is the diameter of the circle, therefore it is absolutely a straight line. Then you extended the straight line EL by straight line, and the result is ET. When you extend the straight line by straight line, the result must be a straight line. Therefore, ET is also a straight line. ET is a straight line, so by doing this construction, we get the quadrangle ETBA. Instead of quadrangle ETBA, we have actually this angle is a right angle because of the fact that ABCD is a rectangle, and we know that all the angles inside the rectangle are right angles. Okay, so this angle is a right angle because ABCD is a rectangle. So in quadrangle ETBA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the big quadrangle ETBA, we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be this right angle if not a square. So in order to quadrangle ETBA is a right angle because it has 4 right angles. So quadrangle ETBA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side AB. So it is known in rectangle ETBA, side ET must be equal to the opposite side AB. ET equals to AB according to the rule that the opposite sides of a rectangle are equal to each other. But according to our definition, AB is the length of rectangle ABCD, so I can write here that AB is the length. And from this equation, ET equals to AB equals to the length of rectangle ABCD, we derive that ET is the length of rectangle ABCD. ET is the length of rectangle ABCD. We also know that the area of rectangle ABCD equals to the length of rectangle ABCD times the width. Okay. In the big right triangle ETG, this angle equals to alpha, this angle equals to 90 degrees, therefore this perpendicular angle must be equal to 90 degrees minus alpha. So actually, it is very easy to see that the big right triangle ETG is similar to the small right triangle EFL. They have exactly the same angles. Actually, this is angle E, that is a common angle that belongs to both triangles. Okay? In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those both angles they are equal to 90 degrees and therefore they are equal to each other. So we can find out that all the three angles in the right big triangle ETG are correspondingly equal to all the three angles of the right small triangle ELF. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle ETG is similar, this is the sign of similar, to the small right triangle ELF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle EFL is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. Repeat again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. ET is the missing side, so we leave it as it is, over EF. It is given as the question that EF equals to 12 units in its length and it is equals to EG. What is the length of EG? EG in total equals to 12 plus 10, that is 22, over EL. EL is the missing side, so we leave it as it is. So in total, we actually found out that ET over 12 equals to 22 over EL. Here we will cross multiply this equation and we get that ET times EL equals to 22 times 12. (22 times 12 is 264 and it is equals to ET times EL. Because again, if you found out that ET times EL equals to 264. We have already found out that ET equals to the length of rectangle ABCD, so we substitute ET by the length of rectangle ABCD times EL. We have already found out that EL is the width of rectangle ABCD. Therefore, we substitute EL by the width and it is equal to 264. The length of rectangle ABCD times the width is the area of rectangle ABCD. That is the area that we are looking for in this question. So, the area of rectangle ABCD, that is the length times the width, is equal to 264 square units. That is the answer to the question. So repeat again, if we found out that the area of this rectangle ABCD, that is the area that we are looking for in this question, is equal to 264 square units. So finish with the first question. In the next step, I will present to you the second question, and we will solve the second question of this lecture. In the second question, our mission is to find out the area of this trapezoid ABCD. Trapezoid ABCD is a right angle trapezoid because of the fact that those two angles are right angles. In addition, you know that side AB of trapezoid ABCD equals to side A to line segment AP. We also know that line segment PD equals to side DC of trapezoid ABCD. In addition, we also know that this is line segment BQ, that is equal to 4 units in its length. This is line segment QC, that is equal to 9 units in its length. Again, our mission is to find out the area of this trapezoid ABCD. Okay. So, first of all, we know that AP is equal to AB. So if we define the length of side AB as A, that is to say side AB equals to A units in its length, then side AP must be also equal to A because they are equal to each other. Likewise, it is given us in the question that side PD, the line segment PD equals to side DC. So if we define the length of line segment PD as B, then the length of side DC must be also equal to B because they are equal to each other according to what is given in the question. In the next step, we will join points B and P together by a straight line. And we join points P and C together by a straight line. By joining points P and B, we created the right small triangle, APB. The right front triangle APB is also an isosceles triangle because of the fact that AP equals to P, AB equals to AP. So we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other and their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other because of the fact that they are located in front of those two equal sides. And we also know that, so if one angle is alpha, then the other angle must be also equal to alpha. And we also know that the sum of the angles in any triangle is equal to 180 degrees. And it is true in any triangle, especially it is true in this triangle ABP. So each angle we have at triangle ABP, we have in triangle APB, we have this angle equals to 90 degrees plus alpha plus 2 alpha. In total, the sum of those angles must be equal to 180 degrees according to the rule that I mentioned. So here we subtract, so 90 degrees plus 2 alpha equals to 180 degrees. We subtract 90 degrees from this equation and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. We divide this equation by 2 and finally we get that alpha equals to 90 degrees over 2 is 45 degrees. So actually this is angle alpha is equals to 45 degrees in its size. And this is also angle alpha that is equal to 45 degrees in its size. So for what we did until now, we can conclude that in any right triangle that is also an isosceles triangle, we have one angle that is a right angle and the two other angles must be equal to 45 degrees each of them. Because of the fact that it is also an isosceles triangle, those two angles must be equal to each other. So if one angle is 45 degrees, then the other angle must be also equal to 45 degrees. We will implement the new rule in our right and isosceles triangle, while PDC. Why triangle PDC is an isosceles triangle? Because PD equals to DC. So those two angles, each of them must be equal to 45 degrees in their sizes. We don't have to repeat on the same process in order to prove that those two angles must be equal to 45 degrees each of them. AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the right side of the straight line AD at point P, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. In this case it means that the implementation of the rule is that the sum of the angles on the right side of the straight line AB at point P must be equal to 180 degrees. So which angles we have at the right side of AD at point P? We have, this is angle, the size of this angle is 45 degrees, so 45 degrees plus 45 degrees is 90 degrees, and 90 degrees plus the size of this third missing angle, in total they must be equal to 180 degrees according to rule 3. Therefore this third missing angle must be equal to 90 degrees in its sides. Why? Because 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles on the right side of the straight line in D at point P according to rule 3. So this missing angle must be equal to 90 degrees in its sides. The missing angle is again BPC, that is the right angle. So we define this angle, that is actually angle QPC as alpha. The big angle is the right angle. Angle BPC is the right angle, and this angle is alpha. Therefore, this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is the size of this, the big angle BPC. We just right now found out that the big angle BPC equals to 90 degrees in its size. So, in the right triangle PQC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this small right triangle PBQ, this angle equals to, before that, we have rule 3, we can implement a rule 3. BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of the straight line BC at point Q? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the small right triangle PQB, this angle equals to 90 degrees minus alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. It is very easy to see that the green small right triangle PBQ is similar to the big right triangle PQC according to angle similarity rule. So why those two right triangles are similar to each other? The green triangle PBQ and the big triangle PQC. Why those two triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So we found out that all the angles of the right big triangle PQC are correspondingly equal to all the angles of the right green small triangle PQB. And therefore, those two right angles are similar to each other according to angle similarity rule. So I write it down. We also found out that the big right triangle PQC is similar, this is the sign of similar, to the right small green triangle PBQ, according to angle similarity rule. Okay, again, if we found out that the big right triangle PQC is similar to the small green right triangle PBQ according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ is a common side that belongs to both triangles. Side PQ belongs to the small green triangle PBQ, and side PQ also belongs to the big right triangle PQC. Okay, so from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PQ of the big right triangle PQC over side BQ of the small right triangle BQP is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PQB. So you can see here that PQ is a common side that belongs to both triangles. Okay. So in total we found out that from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PQB. Okay. PQ is the missing side, so we leave it as it is. Over BQ. BQ equals to 4 units in its length according to what is given as the question. And it is equals to QC. QC equals to 9 units in its length according to what is given as the question. Over PQ. PQ is the missing side, so we leave it as it is. So in total, we have found out that PQ over 4 equals to 9 over PQ. So here we'll cross multiply this equation, and we get that PQ times PQ is PQ squared, and it is equal to 9 times 4, that is 36. So here we'll take a root out of this equation, and we'll get that PQ equals to the square root of 36, that is 6. PQ equals to 6 units in its length. So this is side PQ that equals to 6 units in its length. In the next step, we will implement the Pythagoras theorem on the big right triangle PBC. On this big right triangle PBC. Here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of the big right triangle PBC is BC. The square of the hypotenuse is BC squared, and it is equals to PB squared plus PC squared. And again, according to the Pythagoras theorem, in the right big triangle PBC, BC squared, that is the square of the hypotenuse, equals to PB squared plus PC squared. BC, the hypotenuse BC in total equals to 4 plus 9, that is 13. Therefore, BC squared equals to 13 squared, that is 169. And it is equals to PB squared. What is the value of PB squared? if we focus on the right small triangle APB, we'll implement the Pythagoras theorem on this right small triangle APB. According to the Pythagoras theorem, in this right small triangle APB, a square plus a square equals to pb square. Therefore, pb square equals to a square plus a square, that is 2a square. pb square equals to 2a square plus pc square. What is the value of pc square? We'll focus on the right triangle PDC and we'll implement the Pythagoras theorem on this right triangle PDC. According to the Pythagoras theorem, in this right triangle PDC, PC square equals to B square plus B square. Again, PC square, that is the square of the opposite of the right triangle PDC. PC square equals to B square plus B square. So PC square equals to B square plus B square, that is 2B square. So PC square equals to 2B square. PC square equals to 2B square. So in total we found out that 169 equals to 2A square plus 2B square. So 169 equals to 2. So we take 2 as a common factor out of these two expressions. Inside the brackets we left with A square plus B square. So in total we found out that 169 equals to 2 times A square plus B square. Here we will divide this equation by 2 and finally we get that A square plus B square is equal to 169 over 2. And again, we found out that A square plus B square equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. What is the area of trapezoid ABCD? Actually, we will not use the general formula for the area of a trapezoid. We will do it in another way. The area of trapezoid ABCD is equal to the sum of the areas of the components that trapezoid ABCD consists of. Trapezoid ABCD consists of this right triangle ABP, and the second component is the big right triangle BPC, and the third component is the right triangle PDC. Therefore, the area of trapezoid ABCD must be equal to the sum of the areas of the three components that trapezoid ABCD consists of. So the area of trapezoid ABCD is equal to the sum of the areas of the three components that trapezoid ABCD consists of. The first component that trapezoid ABCD consists of is the right triangle ABP. So it will be the area of this right small triangle ABP. The second component that trapezoid ABC consists of is the big right triangle PBC. So it will be plus the area of the big right triangle PBC, the second component, plus the area of the third component that trapezoid ABC consists of. The third component is triangle PDC, the right triangle PDC. So it is plus the area of the third component, that is the area of triangle PDC. So in total, we found out that the area of trapezoid ABCD equals to the area of the right small triangle ABP plus the area of the right big triangle PBC plus the area of the right triangle PDC. What is the area of this small triangle ABP? It is a right triangle. is equals the area of any triangle equals to the base of the triangle times the height over 2. The base is AB, that is A. The height is AP, that is also A. So it is A times A over 2. A times A over 2 is A squared over 2. So the area of the small triangle ABP equals to A squared over 2 plus the area of the big right triangle PQC plus the area of the big triangle PBC. The big triangle PBC. The big right triangle PBC. What is the area of the big right triangle PBC? It is equals to the base of the triangle, that is BC, times the height PQ over 2. Why the height is PQ? Because of the fact that the height PQ creates 90 degrees with the base BC. This angle equals to 90 degrees. So the area of the big right triangle PBC equals to the base, that is BC, times the height, that is QP over 2. BC, the base, times the height QP over 2. Plus the area of the third component, that is the area of the right triangle PDC. So the area of this right triangle PDC equals to the base, that is DC, times the height, that is DP over 2. The base DC is B, the height DC is also B, divided by 2. So it is B times B over 2, that is actually B squared over 2. So the area of the right triangle PDC is B squared over 2. So in total, if you know that the area of trapezoid ABCD is equal to A squared over 2 plus BC times QP over 2 plus B squared over 2. A squared over 2 plus B squared over 2 is A squared plus B squared over 2. So write it down. A squared over 2 plus B squared over 2 is A squared plus B squared over 2 plus B, the area of triangle PBC, that is BC times QP over 2. BC is 4 plus 9, that is 13, so we substitute BC by 13 times QP. QP is 6, so we substitute QP by 6 divided by 2. So in total, we found that the area of this big right triangle PBC is equal to 13 times 6 over 2. So in total, the area of trapezoid ABCD equals to A squared plus B squared over 2 plus 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. So in total, this expression equals to 39. So in total, the area of trapezoid ABCD equals to A squared plus B squared over 2 plus 39. But we have already found out that A squared plus B squared is equal to 169 over 2. Therefore, we substitute A squared plus B squared in this expression by 169 over 2. A squared plus B squared is 169 over 2 according to this equation. And we have to divide A squared plus B squared by 2. So we make 2 here plus 39. So in total, the area of trapezoid ABCD equals to 169 over 2 times 2 plus 39. So it is 169 over 2 times 2, that is 4, plus 39. Here we will multiply 39 by 4, and then we divide it by 4 in order to have a common factor with this number. And we get that in the numerator, in total, we will get that we will have 169 plus 39 times 4 is 156 divided by 4. And 169 plus 156 is 325 divided by 4. 325 divided over 4 is 81.25 square units. So we found out that the area of this trapezoid ABCD, that is the area that we are looking for in this question, is equal to either 325 over 4 square units, or in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square units. So we finish with the second question. In the next step, I'm sorry, the lecture, we'll start with the first question, of course. In the first question, our mission is to find out the area of this rectangle ABCD that blocks this circle, or this circle is inscribed by rectangle ABCD. In addition, we know that this is called EF, that is equals to 12 units in its length. This is line 7 FG, this is equals to 10 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So, first of all, we know that all the angles inside any rectangle are right angles. So, this angle is a right angle, because ABCD is a right angle. So, here we implemented rule 1. Actually, we defined the radius of the circle as R. We join points O and N together by straight line. Point O is the center of the circle, point N is the point on the circle itself, therefore ON is the radius of this circle that is equals to R according to our definition. And because of the fact that the radius ON that is equals to R, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and M together by straight line. OM is of course the radius of this circle, that is equals to R. Again, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. And finally, we join points O and D together by straight line. O is the radius of this circle, that is equals to R. The radius OE is drawn to point E, that is the point of tendency of tangent AD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius EO. If AD is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees, also according to rule 1. By doing this construction, we can deduct quadrilateral DMON. Inside quadrilateral DMON, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this 4th angle, in total, they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4th angle must be equal to 90 degrees in its size. Likewise, inside the lower quadrilateral EONA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this 4th angle, in total must be equal to 360 degrees, and therefore this 4th angle must be equal to 90 degrees in its size. So we found out that the big angle MON equals to 90 degrees plus 90 degrees, that is 180 degrees. And again, the big angle MON is equal to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size must be a straight line. Therefore, line 7 MON is a straight line. If line 7 MON is a straight line, then MN is also a straight line. And actually, this shape MDAN consists of 4 sides, 1, 2, 3, 4, and therefore it is a quadrilateral. It is a quadrilateral with 4 right angles, and you know that according to rule 5, any quadrilateral that has 4 right angles must be its rectangle if not a square. So we relate to the big quadrangle DMNA, it's a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side DA. So MN equals to DA. But before that, we found out that MN is a straight line. MN is a straight line that touches the circle at 2 points M and N, and therefore MN is a chord. MN is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, MN is the diameter of the circle. And again, MN is the diameter of the circle. And again, DMNA is a rectangle. The opposite sides of a rectangle are equal to each other. So in rectangle DMNA, side MN must be equal to the opposite side DA. Okay, MN equals to DA. And DA is the width and AB is the length. Okay, so MN equals to DA according to the rule that the opposite sides of a rectangle are equal to each other. So in the rectangle BMNA, side MN must be equal to the opposite side DA. But DA itself is the width. So you can write here that the width equals to AD equals to MN. And we already found out that MN is the diameter of the circle. So you can write down that the width equals to DA and AD equals to MN, and MN itself is the diameter of the circle. And in the next step, we extended the radius EO by straight line until it touches the circle at this point. We define the touching point of the extended radius EO with this circle, this point is point L. So we have EL is a straight line because we extended radius EO by straight line. When we extended straight line by straight line, the result is a straight line. So EL is a straight line that touches the circle at 2 points E and L. And therefore EL is a chord that passes through point O. Why it passes through point O? Because we extended the radius EO from point O by straight line. So it is absolutely passes through point O. And we know that any chord that passes through the center of the circle, that is actually point O, must be the diameter of the circle. Therefore EL is also the diameter of the circle. Okay, EL is the diameter of the circle. EL is the diameter of the circle. So in this equation, the width equals to AD equals to MN equals to the diameter. You can write here that the diameter EL is also the diameter of the circle. We just found out that EL is the diameter of the circle. So you can write here that EL is the diameter. And from this long equation, EL equals to diameter equals to MN equals to DA equals to width. So the width, we will derive that EL is the width of rectangle ABCD. Okay? EL is the width of rectangle ABCD. We will derive that EL is the width of rectangle ABCD. Okay? In the next step, we did another construction, that is to say, we extended the diameter EL by straight line until it touches side CB of rectangle ABCD at this point. And we define the touching point of the extended diameter EL with side CB of rectangle ABCD at this point as point T. EL itself is a diameter, therefore it is absolutely a straight line. When you extend a straight line by straight line, the result ET must be also a straight line. Therefore ET is one big straight line. And therefore we have ETBA is a quadrilateral because it has 4 sides. In quadrilateral ETBA we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this 4th missing angle, in total it must be equal to 360 degrees. according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle ETBA, we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be its right angle if not a square. So we write to the big quadrangle ETBA is a right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side AB. Okay? In rectangle ETBA, the opposite sides are equal to each other. That is to say, ET must be equal to the opposite side AB. But AB is the length of rectangle ABCD. So we can write here that AB is the length. And from this equation, ET equals to AB equals to the length. We derive that ET is the length of rectangle ABCD. ET is the length, and EL is the width. Okay. Here we join points L and F together by straight line. By joining points L and F, we can get peripheral angle LFE. This is peripheral angle LFE that subtends on EL, that is the diameter of the circle, and we know that according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. Therefore, peripheral angle LFE must be equal to 90 degrees in its size according to rule 7. So in the right angle EFL, we define this angle as alpha. So this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in the triangle. Likewise, in the big right angle ETG, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Well, because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in the triangle. In the next step, we prove that the big right angle ETG is similar to the small right angle ELF. So why those two right angles are similar to each other? First of all, this is angle E, this is a common angle that belongs to both angles. Angle E belongs to the right small triangle ELF, and angle E, of course, belongs to the big right triangle ETG. So angle E equals to itself is a common angle that belongs to both angles. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So in total, we found out that all the angles of the big right triangle ETG are correspondingly equal to all the angles of the small right triangle ELF. And therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that they are similar to each other, so again, the big right triangle ETD is similar, this is the sign of similar, to the right triangle ELF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side GE of the big right triangle ETG over side EL of the right small triangle ELF. And again, we derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF equals to side GE of the big right triangle ETG over side EL of the small right triangle ELF. ET is the missing side, so we leave it as it is. Over EF. EF is equal to 12 units in itself, according to what is given as the question, and it is equal to GE. GE in total equals to 12 plus 10, that is 22, over EL. EL is the missing side, so we leave it as it is. So in total, we actually found out that ET over 12 equals to 22 over EL. Here we cross multiplied this equation and finally found out that 22 times 12 equals to ET times EL. 22 times 12 is 264, so 264 equals to ET times EL. But we have already found out that ET is the length, so we found out ET by the length, and EL is the width of rectangle ABCD. Therefore, we substitute EL, we substitute EL by the length and ET by the width. Again, ET is the length and EL is the width. So in total we found out that the length of rectangle ABCD times the width is equal to 264. The length times the width is the of rectangle ABCD, and it is equal to 264 square units. So we found out that the area of this rectangle ABCD, that is the area that we are looking for in this question, is equal to 264 square units. We finish with the first question. In the next step, I presented to you the second question, and we solve the second question of this lecture. In the second question, our mission is to find out the area of this trapezoid ABCD. So we know that AB equals to AP, and also know that PD equals to DC. Those two angles are right angles, and this is angle BPC, that is also a right angle. Again, our mission, and we also know that BQ equals to 4 units in itself, QC equals to 9 units in itself. Again, our mission is to find out this trapezoid ABCD. So first of all, we know that AB equals to AP. So if we define the length of AB as A, then AP must be also equal to A because they are equal to each other. Likewise, according to what is given in the equation, PD equals to DC. So if we define the length of PD as B, then DC must be also equal to B because they are equal to each other. In the next step, we join points B and P together by straight line, and join points B and C together by straight line. By joining points P and P, we created the right small triangle PAPB. This right small triangle is also an isosceles triangle because AB equals to AP. Those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other. We know that the sum of the angles in triangle ABP is equal to 180 degrees. That is to say, alpha plus 90 degrees, it is equal to 180 degrees. That is to say, 2 alpha plus 90 degrees equals to 280 degrees. Here we subtract 90 degrees from this equation, and we found out that 2 alpha equals to 180 degrees plus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. Here we divided this equation by 2, and finally found out that alpha equals to 45 degrees. This is again alpha, this is equal to 45 degrees. And this is also again alpha, this is equals to 45 degrees in size. So in total, we can conclude from what we did here that any right triangle that is also an isosceles triangle have 3 angles. One is the right angle, and the 2 other angles, each of them must be equal to 45 degrees. Therefore, this is the right triangle PDC. This is also an isosceles triangle because PD equals to DC. This is the right angle, and those 2 angles must be equal to 45 degrees, each of them. Okay, so in the next step, we focused on the AD is one side of the trapezoid ABCD, therefore it is absolutely a straight line. So we focus on the right side of the straight line AD is point P. Here the sum of the angles must be equal to 180 degrees according to all 3. All 3 says that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AD is point P? We have those 2 angles, 45 degrees plus 45 degrees is 90 degrees, so 90 degrees plus the size of this third missing angle, in total it must be equal to 180 degrees according to all 3. Therefore, this third missing angle must be equal to 90 degrees in its size. Why? Because 90 degrees plus 90 degrees, it is 180 degrees, that is the sum of the angles of the right side of the straight line AD is point P according to all 3. Therefore, this missing angle must be equal to 90 degrees in its size. We define this angle PDC as alpha. Therefore, this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. This is the size of the angle BPC, according to all 3. Therefore, this missing angle must be equal to 90 degrees minus alpha. So in the right triangle PQC, this angle equals to alpha. This angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the small right triangle PBQ, this angle equals to 90 degrees, one alpha, this angle equals to 90 degrees, therefore this this angle must be equal to alpha. Why? Because alpha plus 90 degrees comes alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we prove that the green small triangle PBQ is similar to the big right triangle PQC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, one alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So in total, we found out that all the three angles of the big right triangle PQC are correspondingly equal to all the three angles of the small right triangle PQB. And therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we know that the following relationship exists between their sides. We derive that side PQ of the big right triangle PQC over side PQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. And again, we derive that PQ over BQ equals to QC over PQ. PQ is the missing side of electricities, BQ is 4, QC is 9, and PQ is the missing side. So in total, we found out that PQ over 4 equals to 9 over PQ. Here we cross multiply the equation, and finally found out that PQ squared equals to 9 times 4, that is 36. Here we took out all of this equation, and finally found out that PQ equals to the square root of 36, that is 6. So this is the missing side PQ, that is 6 units. The next step, we implemented the Pythagoras theorem on this big right triangle PBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of the big right triangle PBC is BC, therefore the square of the hypotenuse is BC square, and BC square must be equal to BP square plus PC square. Repeat again, the right triangle PBC, the right big triangle PBC, BC square equals to PB square plus BC square. BC is 4 plus 9, that is 13, therefore BC square is 13 squared, that is 169. So BC square is 169, it is equal to BP square. BP square, if you focus on the right small triangle APB, BP square equals to A square plus A square. So BP square equals to 2A square plus PC square. If you focus on the right triangle PDC, PC square in this right triangle PDC will be equal to B square plus P square, that is 2B square. So PC square equals to 2B square. So in total, 169 equals to 2A square plus 2B square. Here we took out 2 as a common factor from those two expressions, so inside the brackets we have A square plus B square. So in total, we found out that 169 equals to 2 times A square plus B square. Here we divided this equation by 2 and finally found out that A square plus B square equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. The area of this trapezoid ABCD must be equal to the sum of the areas of the three components that it consists of. Trapezoid ABCD consists of the right triangle ABP, and the right big triangle PBC, and the right triangle PDC. So the sum of the areas of those three components, 1, 2, 3, must be equal to the area of trapezoid ABCD. So the area of trapezoid ABCD must be equal to the sum of the areas of the three components that it consists of. The first component is triangle ABP. The second component is the big triangle PBC. And the third component is the right triangle PDC. The area of this triangle ABP is equal to the base, that is 8, times the height, that is A over 2. So it is A square over 2. The area of small triangle ABP is A square over 2, plus the area of this triangle PBC. This equals the area of this triangle PBC is the base BC times the height, that is QP over 2. Again, it is the base BC times the height PQ over 2. And finally, the area of this triangle PDC equals to the base DC times the height DP over 2. So it is B times B over 2, that is B square over 2. there are the right triangle BDC is b squared over 2. So a squared over 2 plus b squared over 2 is a squared plus b squared over 2. BC is 13, PQ is 6 divided by 2. 6 over 2 is 3, and 3 times 13 is 39. So in total, the trapezoid ABCD equals to a squared plus b squared over 2. But a squared plus b squared is 169 over 2. So we substitute a squared plus b squared by 169 over 2, and we have to divide it by 2. So in total, the trapezoid ABCD equals to 169 over 2 times 2 plus 39. So it is 169 over 2 times 2 is 4 plus 39. Here we multiply 39 by 4 and then we divide it by 4 in order to have a common factor with this number. So in total in the numerator we have 169 and plus 39 times 4 is 156 over 2. 169 plus 156 is 325 divided by 2. 325 divided by 2 times 2 is 4. Here we have 4. So in total, the trapezoid ABCD equals to 325 over 4. 325 over 4 is 81.25 square meters. So in total, we should find out the area of this trapezoid ABCD. It is equal to either 325 over 4 square meters. So in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square meters. Okay, thank you very much.